So hey guys, today we are back with yet another video, and this is going to be a research paper based video again, and today's paper is a Hitchhiker's Guide to Scaling Law Estimation. So people who have read about the book, the Hitchhiker's Guide to Galaxy, they must be knowing that what exactly is a Hitchhiker's Guide, and it's a set of, you can say, a book which contains a set of things about the universe, time and space, what intergalactical travel feels like, and what is going to be the ultimate expectation you can keep when you reach a planet. So yeah, something like that. And similarly, this paper is going to be about scaling law estimation, as they say, right? So let's start. So the first thing is, scaling law predicts the loss of a target machine learning model by extrapolating from easier to train models with fewer parameters or smaller training sets. Okay, so they have made it pretty clear in the first line that they are going to show us that a particular set of rules, if they are followed, what are the consequences of that, what are the pros of that, and we can decide ourselves that what is better for us, right? So they say that despite the widespread use of scaling laws, we have seen so much dynamic models that have been there, training and quantization, but there has been little work on understanding how to best estimate and interpret them, right? So they say we use these to estimate more than 1000 scaling laws, then derive a set of best practices for estimating scaling laws in new model families. Okay. Now, I'll try to keep the video as short as possible and show you majorly all the things, the laws that they are talking about, and then you guys can go and see the paper in deep dive and understand their part, right? Now, they say, however, because there is significant degree of variability across model seeds, training multiple models is sometimes more useful than training a single large one, right? We already have talked about this in the previous videos. So this word extrapolation, what does it exactly mean? When we are talking about model training, we are talking about particular set of rules. They are saying when we are estimating an unknown value based on extending a known sequence, right? So that's what they are exactly meaning here for the model perspective. Now, what are they calling a model family? They are calling it a set of models with fewer parameters or smaller training size. Typically, these extrapolating models require models to belong to the same model family. Okay, so little attention is known when training a new LLM. A practitioner with limited computational resources should choose which small scale model to train in order to best estimate a large model's final performance. So maybe they are talking about us, people who don't have much GPU access, but maybe we will have in future when GPUs become cheaper, maybe. So the report, when they say the rest of the paper uses this data to analyze a number of key questions around scaling law estimations. 5 things are there, 5 points, and each of them is important. How reliable maybe we expect scaling laws to extrapolate? So they are saying variation between random parameter initialization can change up to 4% in the loss, right? 4%. And most published improvements procedures when performing minimal control experiments report loss changes between 4 to 50%. So that's a big change. Similarly, how much does the shape of scaling law vary across? They are saying it also depends, because the transformer language models are similar enough with a single model from a target family and the scaling law from a maybe different model family. So somehow it remains the possible to accurately estimate target model performance, right? Now, must scaling laws be estimated only from fully trained models? So same thing that they're going to talk about in future in the upcoming paper part. How large must models be to produce reliable scaling estimates? So they say all else equal, experimenting with large models typically more useful with the smaller ones, right? And the last point, taken together, cost-effective estimation of a scaling law should consider the number of models, the size of models, and the number of training tokens, right? So yeah. Now let's define what is a scaling law. They are saying a scaling law estimates the loss of a costly model by training cheaper ones which share a pre-training token procedure by some hyperparameters, typically model size, the number of tokens during training, the talks, they are saying the parameters, the term using, and the scaling law is a function that predicts a target model's loss on held out data when setting the value of one hyperparameter or both, right? So this mathematics is pretty simple. They are calling a model F, and these are parameters, params, and the number of token stocks, right? Now, there in the coming to the main part, that the scaling law that they are saying here, it's pretty simple, right? This formula they are using. What is A here and B here? We will go up and talk about. So this family will generate the target model whose behavior we wish to predict. That is the F target, right? Second, the Q maximal token family, the max tokens, right? So if you see here, what are these terms? Now here, E is a baseline capturing the scale model's general performance. A, alpha, B, and beta describe the scaling effect of parameters and token respectively. Okay. So these parameters are estimated by first collecting a set of trained models, then minimizing the reconstruction error. So these are the most important formulas that are being used, right? This and this. Okay, cool. Now coming to the next part, that is data for 1000 plus scaling laws and more. They have taken multiple data. They are seeing the models in this data set include ITIA, which provides the largest set of models and variations of family, OPT, and Olmo, Amber, K2, Mamba, Red Pajamas, and they have the overtrained models, Mamba, Llama, and hybrid architecture variations from the transformer architecture. Right? They have Bloom, they have T5, they have the GPT model family with different data regimes. They have the Gopher and GPT-3. Okay. So the data consists of 1.9 million steps of training evaluated on loss or perplexity, usually on multiple data sources belong to 485 unique trained models. If you don't know about perplexity, I made a specific video on that. You guys can go and watch that. Now, coming to scaling law estimations, what they are saying. In the rest of the paper, we present findings from the estimated hundreds of scaling law as follows. Fitting, they are saying, for each model family, we identify the maximal parameter f max is equal to max parameters of f, right? Similarly, f10 is if f, right, the parameter max. And then you have the evaluation. They are doing the same thing, but the 30% maximum token from the f max defined in the previous paragraph, that is that we take f target is the maximum of the tokens, right? Okay, cool. So these are all the assumptions. Now, how well can I expect a scaling law to predict? The first question, right? The first thing that we are going to talk about. From the practice and the training and the experiments that they have done, they are saying empirically we found no widely adopted modeling changes that were motivated with less than a 4% relative difference between models. Additionally, reported variance across random restarts of the model architecture reaches up to 3.5%. You know, it's sort of surprising, but yeah, at the back of the mind, maybe we somehow knew this. Okay. To offer several concrete points of comparison, despite their 6.9 billion models, fixed inconsistencies in their code and hence have two versions, right? Which differ in loss by 40%. Now, just imagine some small inconsistencies that you fixed, right? In the code base, in the data that you have used for training, and you see the differ in loss by 40%. That's a big thing, right? Similarly, they have also data duplication, A/B testing that had a minor effect on the loss of about 5%. This still can be, can be ignored. But how would you ignore this, right? So how well can I expect a scaling law to predict? 4% is the best, and right, typically, and it can go up to 20%. Now, if you guys are thinking that how we are going to do it and what are the estimates that they have already talked about, right? Because if you look at the previous points that they were saying, right, and in most of the cases that they are saying that we have took the model families and worked on how to make sure that the token parameters, everything remains consistent, right? They have used the model family to make sure that the curve fit is remaining on the particular formula that they have defined above, right? So yeah, now coming to below, we'll see some more differences. Start seeing, right? Now, if I take a minute and explain you guys that what exactly are they talking about in this one, when I train a new model, do I even need a scaling law? So now this is a very good question because when we are training a model, right, we most of the time think that, okay, what extra laws that we need to put? Like, we don't think like laws, but the basic consistencies that we have in the previous models, it is there, right? Because if you see here, the absolute relative error here is 4% best, and it can go up to 20%. Just you can string between many modeling choices, right? So they are saying different model families exhibit different scaling laws behavior, but performance can sometimes be estimated using a single model in a new family. They have given an example. One way to answer this question is to look at the parameter estimated for scaling laws. Parameters E, alpha, A, beta, and B across different model families. In the figure 3, they have shown this. Parameters differ between scale model families. Surprisingly, however, the pairs of parameters controlling the influence model and training set size have similar ratios, right? They have similar ratios, and this shows the model architecture, and these are the scaling families, and obviously the right part is the per family intercept. So if you see here the encoder-decoder architecture, two different things, you will somehow see that this decoder, the parameters that you keep increasing, the alpha part, right? It remains, the ratio remains somehow same. Similarly for token parameters and intercept, you will see the same things, right? So yeah, because all the models that they have done here, if you see, all the models, the GPT-2, GPT-3, Gopher, the scale model discrete is that they're saying the intercept part, right? For the E, we have talked about in the previous, because if you see here, what is he? I'll show you guys again. E is baseline capturing the scale model's general performance, right? So in that case, obviously it is making a difference, right? The ratio remains same now. They are saying clearly different pre-trained models with same parameters and tokens still show different loss. So the differences can be consequential, but how do you discrete choice of models? And that is what the answer is. Okay, cool. Now this was one law, and now moving to the next one. But before that, I think one more line we should understand. Another way to answer this question is to ask how reliable we can predict final model accuracy when borrowing some parameters of scaling law between families, even if these result in poor parameters. So to do this, they have set the parameters and the max value tokens to fixed reported values in past work and estimated remaining parameters for individual models. So yeah, for let's say for Olmo family, for example, we obtain less than 1% error estimating accuracy of 7 billion models from a collection of 1 billion model checkpoints. So yeah, however, error rates are larger than in the source family and prediction for larger models. Most consequence in OPT is error of 37, 25, 15 when extrapolating from 8.7, 13, 30 to 175. So you can see the difference, right? It's pretty clear. Now, can I train the target model a bit instead of many small models? Yes, but obtaining reliable estimates in this way require up to 30% of the full training run. So if you can do this, definitely go for this, but if not, no. So because from the figure, I think in the figure in the appendix A, which we'll see at the last, we can clearly see this difference, right? Are even simpler baselines enough? For this, they are saying directly, some extrapolation is necessary. Scaling laws can produce accurate estimates even when the target model vastly outperforms any training model. Specifically, the baselines best performs when you see for the training part, the minimum, and the performance of the most trained model. You will see the similar, right? So baselines are the best performance. So yeah, if you see here in the figure 4, which they are talking about the next one, I have some data. What portion should I use? Estimate scaling loss from intermediate checkpoints, not just fully trained models. So they are making it clear, the intermediate checkpoints, not just fully trained models. So however, some recent work has demonstrated that the effectiveness of learning schedules that do not require prior access to the size of the training set. And some work has questioned whether careful choice of the learning rate decay is necessary for a reliable score. So these are maybe sort of theories you can say, but this is based on the assumption that changes in the learning model which depend on the size of the full data set, right? Should I use all intermediate checkpoints? Almost all, but drop checkpoints from the beginning of training. Okay, yeah, this is pretty clear. Now, next, how big a model should I train? Larger models are better, but not necessary, right? Not necessary. Mainly beware of specific models that have given noisy results. So I'll give you an example. I think Microsoft did this a few years back, maybe 2 years back. They released a model called Phi 2, I think. Yeah, Phi 2. And believe me guys, it was outperforming Llama, I think it was 7 million, I think. Yeah, 7 million, right? I think, yeah. And Phi 2 was, I think, a very small model. It was a 2 billion or 3 billion model. Yeah, 3 billion model. And at that point, 2 years back, a 3 billion model outperforming a 7 billion model was a big thing. And the paper name was Textbooks is all you need. Textbooks is all you need. Right? I think they have a second paper also in this. I think this was only Phi 1 then. Phi 2 was released, and Phi 2 was outperforming a 70 billion model, right? And then Phi 3 came, and it was outperforming again a 70 billion model, right? So, you know, it's not always about the size, but yeah, size is a factor, but not always the size, right? We find that they are the same thing they're saying. Larger models are better, but not necessary. Mainly beware of specific models that might give noisy results. We find that choosing models closer in parameters to the target model is generally effective, but the effect is neither strong nor monotone, right? For example, in all cases, fitting on all F provides one of the lowest absolute relative error. However, in GPT, Gopher and OPT, predicting with the smallest 4 models available is already enough to achieve less than 10% error, right? In Python, the smallest models are not predictive, but the rest of the models provide a similar fit. Similarly, while relying on a larger model is beneficial, predicting many scale laws is still reliable, especially if accounting for the other factor we discussed next, right? So yeah, and I think I'll take 2 more scaling laws. 2 more. So we have the how many models are needed for reliable prediction. 5 model is a safe bet, but more would improve the result robustness. These models can be small. So they say we separate the contribution of size and number of models in figure 1C. We predict with the largest model being held consistent and add smaller models. We see again that larger models do benefit predictions, obviously, but for example, the small models left of the graph, I'll show you this, indicates large errors. However, we do also see the unwanted effects a single model may have on the overall prediction. Okay, cool. If you see here, scale up versus train percentage, models versus train percentage, and models versus scale up predicted, you will see that specific task when you're talking about, you will see some obviously better quality when it comes to smaller models, but overall task, you will see that bigger models obviously have a better point there, right? Similarly, if you can see here, the percentage and the largest model parameter scaling up predicted, right? The 2.7 billion, 6.7 billion, 13 billion model, and you can see the results, right? Because the results like go up, the parameters, right? And the larger model parameters scaled up predicted. So you'll see the same thing here. You will see the patterns remaining somehow same here, right? So yeah, this is how things happen here. Now, if you read what they are saying, the effects of three variables on scaling law accuracy, each cell corresponds to a single scaling law estimate, because this was the part that we were talking about, the AC, right? Models versus scale up predicted, right? We were talking about in the previous one. Now, if you see in the third, the size of the largest model trained expressed as a scale up factor, the ratio between the target and largest model in F train in all laws are estimated for models. All laws use full corpus. Orange line shows a flop continuous, right? Sets of scaling laws whose training sets require the same computation. And if you're wondering what the star is, it represents the most efficient way to obtain that 15%, 10%, and 5% this accuracy, right? The absolute relative error. So yeah, that's how things are. Now coming to the last law, I think we are on. Yeah, last law. So they are saying in the last law, what parameters do I actually need to estimate? Scaling laws might have fewer degrees of freedom than described in, but what they are saying, I'm assuming we do not try to account for aspects other than tokens and parameters. One might wonder if some of the observed errors come from model misspecification, an actual incorrect function from the L. But what they are saying is it's totally dependent, because they are saying first we compute the principal component of 5 learned parameters and find that 3 components explain 99.49% of the variance between 5 parameters. So do we actually need? That's the point. Do we actually need to? Because what parameters do I actually need to? Right? That's the question. So yeah. Coming to the conclusion, they are saying another change for the function that the future might consider is accounting for the learning rate. As scheduled, our experiments assumed it was negligible. It was negligible. Okay. A mismatch between the form and the real dependence might explain the inconsistencies in the beginning of the training. So yeah. Coming to the limitation, they say we use absolute relative error as a primary evaluation metric. That does not distinguish between overestimation or underestimation of performance, right? So yeah, that is one thing that they may improve in the upcoming in the next paper if they are planning on. So yeah guys, I tried to keep the video as short as possible. I just did an overview of the paper because I didn't want to make the video too long, and I would recommend you guys to go and read this paper in detail and learn a lot of new things from this paper. So yeah guys, thank you and have a nice day.